Tonight we're going to look at evidence of what we call the scalar wave phenomenon, and on here on this try we're going to use these two coils of 12-pound 23 gauge wire, about 2.4 Henry apiece, 140 ohms each, 280 ohms of resistance, and we're monitoring then the signal that we're receiving from a helium bulb discharge centrally across the coil. Now here in this example we are looking in the dark here for just video review and saying, well, on this high potential previously shown to be current limited to 7.6 milliamps at wall voltage, which we're presently driving from. The idea here is, if we turn the light on to try to better explain the circuit here, and seeing that we have no cameraman, bear with me. On the edge of the holder there for the coils, I guess we can zoom in a little bit, are two very small red wires, and each of them small red wires, on the bottom example, the small red wire goes directly to the pictured neon tube, and likewise on the other potential the red wire goes to the helium tube. Now on the opposite ends of these tubes go to a destination of air plate capacity, here pictured simply made from foil around a pizza box on the adjacent chair. Now the problem being here on these investigations is the simple fact that both the plates and the bulbs themselves emit RF. On this example here we're going to be able to show that because the source endings on both of these tubes being to the right on the picture and having destinations to the left, each of them bulbs are emitting a radio wave that the coils pick up in opposite polarity. So now we'll go around there and look and see what that opposite polarity looks like, and thereby prove some simple things at least by the demonstration. But watch out for me. Watch. Didn't know what I'm doing, but you're trying well. Okay, here then. Here we also have an asymmetrical amperage delivery to the plates. There's a 0.06 milliamps going from the longer helium bulb of more resistance. It's only 0.04 milliamp going through the neon in the background. Now what we're going to have to try to do then is gently set the tripod down and try to get this thing focused into the scope, which hopefully won't just take in a second. Get my tripod in my regulars down. Who are you looking here? Very good, eh? Okay. I suppose then for the camera illustration then, what we need to be doing, we're going to be turning out the neon bulb by hand, and it looks like that's a pretty good zoom point, and we can get by with not to be a perfectionist, but here we can do with this, I would imagine. Now if you'd be looking at the scoping, you can see that there's two counterpart waves of RF being picked up by the coil system, and one counterpart seems to be opposite in time to the other counterpart. So to prove that that opposite counterpart is being made by the bulb RF coming from the outside bulb versus the inside bulb, all we got to do now is just disconnect the bulb and show the difference in the scopings. We might need some better light for that. Then we can probably conclude here. That looks like that's working pretty well. We'll try extinguishing the neon bulb. As we can see, the opposite signature went away. But of course most amusing then, since we connected it from the ending that is going to its applied capacity, there's still quite a bit of illumination on that bulb. Hence why did not the cancelling signature appear? Okay. So when you're investigating these things, they throw all kinds of loops. There's a lot of contradictory information. We'll hook that back up again. Once again, our counterpart wave appears. I'm going to try to conclude, maybe get a better scoping of that wave. Unfortunately, that's at 5 volts per division, meaning I got to change the probe setting to get a smaller signal. So we'll try that one more time. I'll be disconnecting the bulb. Vanishing complementary signature, however we still have bulb ignition. Now according to theory we might think that if we reverse the bulb connection, if that's possible in this dim light, these currents can be felt to be vibrate by hand easily. So now we're going to put the bulb in the other condition. I can't quite connect it. It looks like that's it. And then that's what we get with the other situation. So the evidence seems very contradictory, but yeah, we can cite the influence of an outside bulb voltage and display this kind of effect at the high frequency sweep, which I didn't mention. I'll turn the light on again and do, come on light, and do a range sweep down on what we're observing. This is what we're looking at, a so-called scalar effect there, right? Okay, then we're at 50 microseconds per division, 5 volts per division deflection, full screen deflection. Now we'll be going down to 0.1 millisecond. 0.2 millisecond. 0.5 millisecond. 1 millisecond. And we can see from the long length of wire is the receptor that we're filling up quite a bit of the time spectrum allotted for these high frequency events to occur. And finally we can go down to 2 milliseconds and see 3 high frequency events per 60 Hertz cycle occurring in a somewhat multiple fashion. And then again we can disconnect the outside bulb influence to see any possible difference in interpretation. Then we can, of course, analysis will be incomplete without doing a scope adjustment on each channel. But I think we've shown enough there about this so-called scalar effect and how it might be interpreted. Thank you.